Welcome to our deep dive into support vector machines, or SVMs. In this video, we'll unravel the core concepts behind one of the most powerful and popular algorithms in machine learning. Whether you're a beginner or looking to refresh your knowledge, this journey will help you understand how SVMs work, why they're so effective, and where they're commonly used. Let's start by exploring what makes SVMs unique compared to other classification algorithms and set the stage for a detailed exploration of their inner workings. Support vector machines are supervised learning models used for classification and regression analysis. At their core, SVMs aim to find the best boundary or hyperplane that separates different classes in your data. This boundary is chosen to maximize the margin between the classes, making SVMs robust and effective, especially in high-dimensional spaces. In the next scenes, we'll break down how SVMs achieve this and why maximizing the margin is so important for generalization. Imagine you have two groups of points on a plane. The SVM algorithm looks for a line, or in higher dimensions, a hyperplane that best separates these groups. The ideal hyperplane is the one that leaves the largest possible gap between the two classes. This gap is called the margin. By maximizing the margin, SVMs help ensure that the model not only fits the training data but also performs well on new, unseen data. Support vectors are the data points that are closest to the hyperplane. These points are critical because they directly influence the position and orientation of the hyperplane. If you were to remove a support vector, the hyperplane would shift. This unique property makes SVMs highly dependent on these key data points, and it's why the algorithm is named after them. SVMs can handle both linear and nonlinear classification problems. For linearly separable data, a straight hyperplane works perfectly. But what if your data isn't linearly separable? That's where nonlinear SVMs come in, using clever mathematical tricks to transform the data into a higher dimensional space where a linear separator can be found. This flexibility makes SVMs suitable for a wide range of real-world problems. Magic behind nonlinear SVMs is the kernel trick. Kernels are mathematical functions that allow SVMs to operate in high-dimensional spaces without explicitly computing the coordinates of the data in that space. This means SVMs can efficiently find complex boundaries between classes, even when the data is not linearly separable in its original form. There are several types of kernel functions commonly used in SVMs. The linear kernel is the simplest, suitable for linearly separable data. The polynomial kernel allows for more complex boundaries, while the radial basis function (RBF) kernel is popular for its ability to handle highly nonlinear data. Choosing the right kernel is crucial for the performance of your SVM model. SVMs are most widely used for classification tasks. Whether it's spam detection, image recognition, or medical diagnosis, SVMs excel at drawing clear boundaries between classes. Their ability to handle high-dimensional data and avoid overfitting makes them a favorite among data scientists for many real-world applications. While SVMs are famous for classification, they can also be used for regression tasks. This variant is known as support vector regression (SVR). Instead of finding a hyperplane that separates classes, SVR finds a function that best fits the data with a margin of tolerance. This makes SVMs versatile tools for both classification and regression problems. SVMs offer several advantages. They are effective in high-dimensional spaces, robust to overfitting, and work well even when the number of dimensions exceeds the number of samples. Their reliance on support vectors makes them memory efficient, and the use of kernels allows them to model complex relationships in data. Despite their strengths, SVMs have some limitations. They can be less effective when the data set is very large, as training time increases significantly. SVMs also struggle with noisy data and overlapping classes, and choosing the right kernel and parameters can be challenging. Understanding these limitations helps you decide when SVMs are the right tool for your problem. Support vector machines are used in a variety of real-world applications. From handwriting recognition and face detection to bioinformatics and text categorization, SVMs have proven their value across industries. Their ability to handle complex, high-dimensional data makes them a go-to choice for many challenging tasks. One classic application of SVMs is handwriting recognition. By analyzing the pixel values of handwritten characters, SVMs can accurately classify letters and numbers. This technology is widely used in postal services and digital note-taking apps, demonstrating the practical power of SVMs in everyday life. SVMs play a key role in face detection systems. By learning the differences between face and non-face images, SVMs can quickly and accurately identify faces in photos and videos. This capability is essential for security systems, social media platforms, and smartphone cameras. In bioinformatics, SVMs are used to classify proteins, genes, and other biological data. Their ability to handle high-dimensional and complex data makes them ideal for tasks like cancer detection, gene expression analysis, and drug discovery. SVMs help researchers make sense of vast amounts of biological information. Text categorization is another area where SVMs shine. By analyzing word frequencies and patterns, SVMs can classify documents, emails, and web pages into categories like spam or not spam, sports, or politics. This is crucial for organizing information and filtering unwanted content. SVMs are widely used in image classification tasks. By extracting features from images such as edges, textures, or colors, SVMs can categorize images into different classes. This technology is used in everything from medical imaging to self-driving cars, where accurate image recognition is critical. Spam detection is a classic use case for SVMs. By analyzing the content and structure of emails, SVMs can distinguish between spam and legitimate messages. This helps keep our inboxes clean and protects us from phishing attacks and unwanted advertisements. SVMs are increasingly used in medical diagnosis, helping doctors identify diseases from complex data like medical images or genetic information. Their accuracy and ability to handle high-dimensional data make them valuable tools in healthcare, supporting faster and more reliable diagnoses. In finance, SVMs are used for tasks like stock price prediction and credit risk assessment. By analyzing historical data and market trends, SVMs can help financial institutions make better decisions and manage risk more effectively. Speech recognition systems use SVMs to classify sounds and words. By analyzing audio features, SVMs can distinguish between different speakers, languages, or commands. This technology powers virtual assistants, transcription services, and voice-controlled devices. SVMs can also be applied to time series analysis, such as predicting trends in weather, sales, or traffic. By modeling patterns over time, SVMs help businesses and organizations make informed decisions based on historical data. Selecting the right parameters is crucial for SVM performance. Key parameters include the type of kernel, the regularization parameter C, and kernel-specific settings like gamma for RBF kernels. Tuning these parameters helps balance model complexity and accuracy, ensuring the best results for your data. Cross-validation is a technique used to evaluate SVM models and select the best parameters. By splitting the data into training and validation sets, you can test how well your model generalizes to new data. This helps prevent overfitting and ensures reliable performance in real-world scenarios. Feature scaling is important when using SVMs, especially with kernels. Scaling ensures that all features contribute equally to the result, preventing features with larger ranges from dominating the model. Common techniques include normalization and standardization. Imbalanced data can pose challenges for SVMs, as the algorithm may favor the majority class. Techniques like resampling, adjusting class weights, or using specialized metrics can help address this issue, ensuring fair and accurate classification for all classes. While SVMs are inherently binary classifiers, they can be extended to handle multiclass problems using strategies like 1vs1 or 1vsrest. These approaches break down multiclass tasks into multiple binary classification problems, allowing SVMs to tackle more complex scenarios. Soft margin SVMs allow for some misclassification in the training data to achieve better generalization. By introducing a regularization parameter, the model balances maximizing the margin with minimizing classification errors. This approach is especially useful when dealing with noisy or overlapping data. Hard margin SVMs require that all data points be correctly classified, with no errors allowed. This approach works well for perfectly separable data but can lead to overfitting and poor performance with noisy or overlapping classes. Understanding the difference between hard and soft margin SVMs is key to choosing the right model. Training an SVM involves solving an optimization problem to find the hyperplane that maximizes the margin. This is typically done using quadratic programming techniques which efficiently handle the constraints and objectives of the SVM model. Optimization is at the heart of SVM training. The dual problem is an alternative formulation of the SVM optimization problem. By expressing the problem in terms of Lagrange multipliers, the dual form allows for efficient computation and the use of kernel functions. This mathematical trick is key to the power and flexibility of SVMs. Not all data points become support vectors. Only those that lie closest to the margin or violate the margin constraints are selected. This selective approach keeps the model efficient and focused on the most informative data points, reducing memory and computational requirements. The SVM decision function determines which side of the hyperplane a new data point falls on. By calculating the weighted sum of support vectors, the model predicts the class of the input. This function is fast and efficient, making SVM suitable for real-time applications. Regularization is a technique used to prevent overfitting in SVMs. By adjusting the regularization parameter, you can control the trade-off between maximizing the margin and minimizing classification errors. Proper regularization leads to models that generalize well to new data. SVMs are particularly effective in high-dimensional spaces, where other algorithms may struggle. Their reliance on support vectors and the use of kernels allow them to find clear boundaries even when the number of features is very large. This makes SVMs ideal for tasks like text and image classification. Training SVMs can be computationally intensive, especially with large datasets. The complexity depends on the number of samples and features as well as the choice of kernel. Efficient algorithms and hardware can help speed up training, but it's important to be aware of these challenges. Several software libraries make it easy to implement SVMs, including scikit-learn in Python, libsvm, and others. These libraries provide efficient implementations, parameter tuning tools, and support for various kernels, making SVMs accessible to everyone from beginners to experts. Visualizing SVMs can help you understand how the algorithm works. By plotting data points, hyperplanes, and support vectors, you can see how SVMs separate classes and maximize the margin. Visualization tools are invaluable for learning and debugging SVM models. How does SVM compare to other machine learning algorithms? SVMs often outperform algorithms like logistic regression and decision trees on high-dimensional data. However, they may require more tuning and computational resources. Understanding these trade-offs helps you choose the right tool for your task. The future of SVMs looks promising with ongoing research into faster algorithms, better kernels, and new applications. As data grows in size and complexity, SVMs will continue to evolve, remaining a valuable tool in the machine learning toolbox. With the rise of deep learning, SVMs are sometimes overshadowed by neural networks. However, SVMs still offer advantages in certain scenarios, such as smaller datasets or when interpretability is important. They remain a relevant and powerful option for many tasks. Interpreting the results of an SVM model involves understanding the support vectors, the margin, and the decision function. By examining these elements, you can gain insights into how the model makes predictions and identify areas for improvement. Common pitfalls when using SVMs include improper parameter tuning, ignoring feature scaling, and using the wrong kernel. Being aware of these issues and taking steps to address them can help you build more accurate and reliable models. To get the most out of SVMs, follow best practices like proper data preprocessing, parameter tuning, and cross-validation. Regularly evaluate your model's performance and be ready to adjust your approach based on the results. These habits will help you build robust and effective SVM models. Support vector machines are a cornerstone of modern machine learning, offering powerful tools for classification and regression. By understanding their core concepts, strengths, and limitations, you can harness the full potential of SVMs in your projects. Thanks for joining us on this journey through SVMs. Keep exploring and applying what you've learned.